Hi, this is your pal Dr. Sal, and today we're talking about math and how much math you would need to know as a doctor. Now, I'm just going to run a quick number series and tell me if you can find the pattern. 28, 56, 84, 112, 140, 168, 196. Now, for those math whizzes of you out there, you would realize that this is your 28 times table. Now, why would I, as a practicing general practitioner, family doctor, know my 28 times table? Turns out there's a good reason for that, and I'm going to explain that in this video, what math doctors tend to be good at and what math we're not good at and why. So first off, I just want to give a shout out to some of my favorite authors. Unfortunately, in many of their publications, they often portray doctors as math buffoons. For example, I've seen it in some of Malcolm Gladwell's work. I've seen it in Daniel Kahneman's book, Thinking Fast and Slow. And I've also seen it in my favorite author's book, Nassim Taleb, in his book, Anti-Fragile. Now, it's not that these guys are wrong, but I think they're kind of missing the point because they're not working in my industry. Do I really need to be able to solve your taxes to be able to figure out what medication to give you? Do I really need to be able to calculate Earth's gravitational constant to be able to tell you need to lose weight? So that's being a little tongue-in-cheek. In this episode, what I'm going to try to do is show you what type of math doctors tend to shine at and what types we tend to falter in and why. But before I go into that, it's important to understand that this is a generalization. There are subspecialties in medicine. For example, epidemiologists are math rock stars. They could go head to head, toe to toe with any math major any day of the week and knock them out. But in general, most of us get floppy with our math after graduation because it's generally not required in what we're doing. I'm going to divide math in general into 6 different units, and I'll start with the 3 that we tend not to be so great at, and then the other 3 that we're pretty hot at. And at the end, I'll show you why I know my 28 times table. And it's because it's useful to me, and I'll show you how. So all these 6 categories, we do have to learn to a T in our undergrad experience, in our undergrad education. But it basically withers after we finish cramming it and go into med school and eventually graduate because of disuse atrophy. It's just like any other muscle. If you stop using it, it withers away. It's no different for your math muscles. So the first category that I'll talk about for math would be Newton's favorite, the stuff he calculated, him and Leibniz, calculus. So in case you're not familiar with calculus, that's where you're determining, basically taking complex relationships and dividing them into little tiny slices, or adding up lots of little slices. So it's useful, for example, calculating volumes of strange odd shapes, and also for calculating things like rates of change, so like acceleration, velocity, etc. Now, in the last decade of being in practice, I have not had a single occasion where I needed to calculate somebody's rate of change in velocity or calculate the volume of a cone. So calculus to me has paid 0 dividends as an actual medical doctor in practice. That being said, though, it's still useful knowing the concepts of for example, the small changes, say like dx, dt, versus integration where you're summating smaller groups. Understanding those concepts is useful, but as I'm not an engineer, I'm not designing bioprosthetics and so forth. So calculus for me has turned out to basically be pretty much a waste of time learning all the nitty-gritty and all the nights I wasted sweating trying to do all these different calculations. That being said, though, you still have to go through it as part of your undergrad, especially if you're doing physics. The second category of math that I find that we really don't shine at is algebra, and the other one is trigonometry. Now, again, the reason for that is real simple. So the algebra is stuff like 2x plus 5y equals 15, solve what x is or something like that. No, in real life, we don't come across artificial scenarios like this. We use measurements, so there's no x's, there's no y's, because we measured everything. So algebra, again, in the last decade of practice, I haven't had any circumstances where I needed to apply any algebra whatsoever. Same thing for trigonometry. Trigonometry, we're looking at if you know the radius of a sphere, what's the units if you were to circumnavigate that sphere? Well, again, in practice of medicine, figuring out perimeters of cubes and stuff really isn't very useful and it's not pertinent. So again, this stuff here, as time goes on, it basically fades from our memory because we don't use it. Not to say that at one point we couldn't use it. It's just that by the time those authors that I mentioned earlier and the studies that they quote, by the time they test us on those things, after we've been in practice 5, 10, 20 years, obviously we're going to score badly because we never use those things. So I think the media in general tends to not get that. The third thing, and this one is kind of sad to me, another one that we tend not to be that great at is stats and probability. Again, this is in general. There are some rock stars in medicine that know this stuff inside and out and could step to any PhD in math with them. But the reason why it makes me a little sad there is with the probability, believe it or not, most of the foundation of probability science was started by a physician by the name of Cardano sometime after the time of around Leonardo da Vinci. He's another Italian, and believe it or not, his name really was Cardano, and he was a card shark. But he was an itinerant gambler in addition to being a physician, and he studied things like he started the ideas of things like sample spaces, and if you roll a die so many times, what's the mathematical chance you're gonna get sixes 3 times and that kind of stuff. He was the first guy that put that kind of what appear to be random events on a mathematical foundation. So every casino you see in the world today is still using the basic tenets that he originally came up with. Unfortunately, his descendants today in medicine generally tend not to do so well on tests of stats and probability. Now, another insider secret I'm going to share with you is why we tend not to be so great at these numbers. So all these media things that you'll see or Google that show doctors as buffoons, I'll show you why that's the case. Is because we don't need it. And I'll show you an example here. We have whole staff that work with our colleges and universities and stuff that employ mathematicians and people with math backgrounds and physicians that have studied statistics and that do more academic stuff to go through all these different complex studies and then share with us succinctly the basic findings of the studies. So to give you an example, this here is an example of a study about gout and diet. So gout's just a condition where you get some real painful toes and knees. And the basic summary here in bold is that a higher DASH dietary, that's a type of diet, but I'm not going to go through that right now, was associated with a lower risk for gout. Real simple. Everything in bold here. This is just one paragraph that I need to read between my busy day to figure out, okay, if I have patients with gout, I need to put them on a DASH diet. Don't need to be a genius to figure this out. Now, compare that to what the original article looked like that these guys had to summarize for us. So I'm just going to show you the original article here. So it was published in the British Medical Journal, which I actually wrote a few articles for before as a med student. Whoops. Uh-oh. Sorry, let me just pop that there. So this is the original journal article here. So here we go. I'm going to start scrolling. Look at that. yawn. Ooh, my eyeball's already starting to burn. And it just keeps going and going and going and going. And then on top of that, then is all these numbers, and it's just wow. Oh my God. We're not even halfway through the journal yet. Look at all these numbers there to burn the eyeballs. And then we're still only about 1/3 of the way through. Then there's all these graphs here. Oh, and it just keeps going and going and going and going and going. And this is just an example of one article. That's just one article. So obviously, being a busy practicing physician, if you give me this versus the one-page summary, I'm going to take the one-page summary. I got other things to do, like treating people. So after a while, our math muscles get flabby when it comes to calculating all these p-values and standard differentiation and variance and all that stuff. Why would we need it when we have people doing it for us already? I remember anecdotally a story of Henry Ford, where he was in court. Somebody was accusing him of being a dummy. And he basically explained that he didn't need to know this stuff that they were alleging he should know, because he had 10 men that he has hired that he could just point a finger at and say, hey, give me this information. So it's very similar with medical doctors. One thing people don't realize is for most family doctors, their vision of hell is to be on a deserted island with a bunch of these journals to read all day. So that's part of the reason that if you then go and run a random study on us and see how good we are at calculating different probabilities and stuff, we tend to do dismally. And it's because we don't need it. Now, there is one instance where I think doctors could do a lot better, not so much in terms of stats, but in terms of probabilities. And that's in explaining to people their risk for certain procedures. Up to yesterday, I saw a lady that came in, and she had seen a urologist, and he was trying to explain to her the risks of undertaking a certain procedure. So she said that by the time she got back to her vehicle, she thought to herself, wow, if I do this procedure, I'm gonna die and I'm never gonna be able to have sex again. The problem in the way this guy presented the risk to her is that he didn't provide any context. There was no base rates associated. He just said, look, if I do this procedure, there's a chance you could die, there's a chance you're gonna have pain and intercourse for the rest of your life, blah, blah, blah. And generally that's not very useful, because if I tell you going on an airplane, there's a chance you could crash and die, there's a big difference between if that chance is a 1 in 2 chance or a 1 in 2 million chance. In the former, I'm pretty sure you're gonna walk instead of taking the airplane. So it's very similar with coding risk to surgical procedures. I find very often my colleagues do not code the base rates very well. So people don't have a very good impression of the risks or the minuscule risks involved in some of these surgeries. And even worse, I've had more than one patient, several patients coming back after seeing back specialists, orthopods, and then being told that if they get whatever surgery it is that they were considering, that there's a 50% chance that they might not walk again after the procedure. Well, that is absolute bollocks. To tell somebody there's a 50% chance they can't walk again after having a dysfusion or a discectomy or whatever it is, it would mean that out of every 2 patients that surgeon was seeing, one of them never walks again. Now that would be the most heinous, egregious malpractice on the planet. If these procedures were that risky, they would be outlawed. So that would be my main critique of my industry when it comes to probability. Now, 4th category of math that I can consider is graph theory. And actually, I recently learned something about this that was pretty neat. I saw in some documentary that the graphs, which were invented by a French mathematician, Descartes, he originally came up with the idea while he was laying in bed and saw a fly flying around over his bed head. And as he was trying to trace his trajectory, he came up with the ingenious solution of of drawing the fly's path on a set of axes, the number line system that we use. So as you saw in the earlier journal that I showed you there from the British Medical Journal, you saw that there was a bunch of graphs in it. We're very used to seeing graphs because we're always seeing graphs of like drug reactions, people's growth charts. We're always using graphs. So I would say most doctors are very familiar and very adept at using graphs and reading graphs. And that's because we use them often. The next math that I look at, that I would say we're pretty good at, is units and measurement. We're always using different units like Celsius, Fahrenheit, interconverting them pounds to kilos and vice versa. So we're pretty adept at thinking in different number units, and we're also pretty good at understanding different forms of measurement. And again, that's because we're always doing measurement. We're measuring in cc's or mils or kilos and pounds and stones. So I would say this is another area where we tend to shine at is being able to use different units of measurement. The next form of math that we're good at, again because we need to be, is arithmetic. And a lot of this arithmetic is basically like grade school level, but arithmetic is super useful in practice of medicine. We're always adding things up and subtracting things and multiplying things. And to let you in on the little secret of why I know my 28 times table, that again comes down to arithmetic. And the reason why I know my 28 times table is because it's useful. Because each month in the year has a different number of days. So very often when we're prescribing high value or controlled substances like Ritalin derivatives or opiates, painkillers, rather than leaving things open to chance and writing, say, 1 month of whatever, we'll actually write 28 days worth, so that it's very precise when it gets to the pharmacy. And it also means that if I give you a prescription today on a Tuesday, 28 days later will also be a Tuesday, and 28 days after that will also be a Tuesday. If I write you a 30-day supply, 1 month you're going to be coming in Tuesday, the next month you'll be in on a Sunday, and then the next month is some other day again. So it's chaotic when you do 30-day supplies. So the 28-day system comes from the fact that each week has 7 days in it, as we all know, and there's 4 weeks in every month, which then leaves you magic 28. Then the reason why I know the 28 times table is because based on this base number of 28, if I'm giving you, say, 1 tablet of something a day, so say I'm giving you 1 tablet of morphine a day, then I immediately know for a month you're going to need 28 tablets. If I'm giving you 2 tablets a day, then I know you're going to need 56. And I've written these so many times on prescriptions that it's just burned into my memory, the 28 times table now. If I give you 3, I immediately know that's going to be 84. If I give you 4 tablets a day, I know that's going to be 112. If I'm giving you 5, immediately know that's going to be 140, and if I'm giving you 6 tablets a day, I immediately know that's going to be 168, blah blah blah. That's why it's in my memory. So medical doctors, just like everybody else, we keep the things that stick in our mind are the things that we use on a regular basis and things that are useful. Now remember, if you're considering medicine as a career, you're still going to have to be exposed to all these things, even though some of them are going to be of very little value to you later. It's just part of the rite of passage that universities require you to know all this stuff. I have not ever in my career as a medical doctor had to calculate how much energy I would need to launch you in your living room chair off into orbit. What I'm interested in is stuff here on Earth, the real practice of medicine. So don't be dissuaded from a career in medicine if that's what you were considering by watching this video. A lot of these things you just have to scarf them down for the moment. Later on, after you cram them and pass them, then most of it just fades off over the horizon. So thanks very much for watching. That is math in medicine. And I hope that helps to dispel some of the media nonsense about doctors being horrific at math. To some degree, we are, but it doesn't matter because we're not mathematicians. We're not solving your taxes for you. We're not out there engineering better seatbelts. It's not pertinent to our industry. So don't be fooled by those studies that you see out there. We're still very competent at what we do, but we focus on what we really need. Thanks for watching.